In this video, we will investigate several antiderivatives involving general exponentials. So as a reminder, we've previously generated the formula that the antiderivative of a to the x is 1 over ln of a to the x, plus c. Now, note one can always check that this formula is true. So if you forget maybe what the constant out front is supposed to be, is it ln a, 1 over ln a, we can always check. So the derivative of that function on the right should be the integrand a to the x. So the derivative of 1 over ln of a to the x, you think 1 over ln of a is a constant which pulls out front. And then you multiply this by the derivative of a to the x, which we previously said is ln of a to the x. The 1 over ln of a and the ln of a cancel. And what we're left with is the integrand a to the x. So let's go ahead and put this to work. One of the most common mistakes I see involving integrating or anti-differentiating general exponentials is maybe mistaking when you are dealing with them. So x to the fifth versus 5 to the x. When you anti-differentiate x to the fifth, you're just undoing the power rule. This is what we've been doing since Calculus 1. 5 plus 1 is 6, so 1 6, x raised to the 6. Plus the antiderivative of 5 to the x. 5 to the x is an exponential function, so we use our new formula. 1 over natural log of 5, 5 to the x, plus c. All right, so a second example here, a definite integral. So to anti-differentiate 2 to the s ds, so s is our variable of integration, and recall it doesn't matter which variable we use, s, x, t, as long as we're consistent throughout. So using our formula, the antiderivative of 2 to the s would be 1 over the natural log of 2 to the s, and by the fundamental theorem of calculus, we evaluate from 1 to 2. So we replace s with a 2, put a minus sign, replace s with a 1. So we have 2 squared minus 2 to the 1. So 2 squared is 4, minus 2 is 2. So we end up with 2 divided by the natural log of 2. And one more example here involving, once again, a definite integral. And looking at the form that we have, 5 raised to the square root x divided by the square root x. This is similar to an example we've previously encountered involving the exponential function e raised to a power. The observation that I make looking at this is you have square root x inside the exponential, and up to a constant, it's missing, say, a 2 here, its derivative appears outside. So this looks like something where a u substitution would work very nicely. If u is the square root of x, du is 1 over 2 square roots of x dx, so that in our case 2 du is going to be 1 over square root x dx. So in terms of taking the integrand and writing it solely in terms of u, the square root of x becomes u, and then the dx over the square root of x is going to be 2 du. So pulling out the constant 2, we have a definite integral with limits of integration that we need to determine, but what we're integrating is simply 5 to the u. So let's think about our limits of integration. So we need to change these. So in terms of x, the lower limit of integration is 1, and looking at our substitution, when x is 1, u is also going to be 1. So x equals 1 implies u equals 1. And for that upper limit, when x is 4, we have u as the square root of 4, which is 2. So our limits of integration in terms of u is simply 1 to 2. And recall, if you're using a u substitution with a definite integral, the two integrals that we have, the first in terms of x, the second in terms of u, are equivalent. So once we evaluate this new integral, that is our solution. We are done. So let's anti-differentiate. The antiderivative of 5 to the u is 1 over natural log 5, 5 to the u. And by the fundamental theorem of calculus, we evaluate from 1 to 2. So 2 over natural log of 5 is a constant. We replace a u with a 2. We put a minus sign and replace it with a 1. So 5 squared minus 5 is 20. 20 times 2 is 40. So our simplified solution here would be 40 divided by the natural log of 5.